Okay. Hi, everyone. My name is Cale Plut, and I'm here today to talk about my PhD thesis on the application and evaluation of affective, adaptive, generative music for video games. Let's begin. So the main research question that we're trying to answer with this work is how can we use generative music in games? Along the way, we have some sub-questions to answer. Does adaptive music influence player emotion, and how can we model gameplay for musical adaptivity, specifically based on that emotion? We'll explain why we do emotion in a bit. We also have the question of how can we control game music to express a particular emotion, both for composed and generative music. And then finally, how can we compare our approach to current game music? For our contributions, we have helpfully separated them out by paper here. We have our state-of-the-art paper in which we survey trends in both academic and industry approaches to using generative music in games. We do a study on the perception of adaptive music and find that players do perceive when music adapts based off of an emotional model of gameplay. We create a real-time perceived emotion model with Preglam, which watches a game and tries to output a perceived emotion of the gameplay. We produce the ISOVAT affective composition guide, which places a set of musical features and describes how changing those musical features can change the perceived emotion. And then we put this all together and apply a generative model to create a real-time generative adaptive score based off of affect. And then we evaluate our use in comparison to a linear and adaptive composed score that share similar production techniques. So the first question we have to answer when we're using music in games is, what is the function of the music going to be? What is the music trying to do for the game? And I'll note here that there's not really any established terminology in this field. We just have here from two books, lists of two different sets of game music functions, and we'll note that none of the terminology is the same, although I've tried to use icons here to demonstrate when there is some conceptual overlap. The function that we're specifically focusing on with this work is music acting as an audience. Winifred Phillips describes this as though the music should feel as though it's watching the gameplay and commenting periodically on the successes or failures of the player. We've interpreted it in this little comic way as imagining that if there is a player playing the game, that it's as though there's a musician sitting next to the player and watching them play the game and playing music along with what's happening. I'll note that this is similar to some previously existing musical performance practices. So early silent films, the audio and video could not really be automatically synchronized. And so live musicians had to have ways of stretching or compacting music to match what's happening in a film. And then in live theater, there are times where, especially in musical theater, there are times where there are scenes or something happening on stage where the timing is not exactly determinate in advance. And so the orchestra has to be able to respond to the input of how long the scene is actually taking. So they have this thing called a vamp, where the way this would work is that the orchestra would repeat these two measures while a scene is happening. And then if the actor says the cue line, which in this case is traveling on business, the orchestra plays the stinger and moves on. Now, it's not quite feasible to ship a entire musical ensemble with every sold game, so we have to do this in an automated way. And what we do is we use this technique in games called adaptive music, which basically takes the idea of vamps and really extends them pretty much as far as they'll go, where almost an entire score can now be cut up into 4-bar measures or 8-bar measures that can rearrange and be placed at various points in times and have instruments entering and exiting based off of what's happening in the gameplay. Now, the pro of using adaptive music is this really does allow us to have music that matches previously unknown input. The problem with adaptive music is that in order to write adaptive music and create musical adaptivity, there are some additional musical constraints about what can be written when, because clips have to be able to transition to each other even when you don't know when they're going to transition or which clips are going to be transitioned to or from. And so this places some constraints on the composition, and then also often you have to write more music, or you have to do more work for the music per time because you'll have to write, say, multiple variations for any particular clip. And so this takes more time, this takes more work, and time is money. And then on top of this, audio and music in the games industry is generally on the bottom of the priority pile. So adaptive music tends in the industry to be very simply used, and we'll talk about that a little bit in the future as well. Now, generative music seems to be the solution to these cons of adaptive music. Depending on the algorithm that you're using for generative music, these algorithms can create music very fast. They can create a lot of music, and they can create music with constraints without really any additional problems. There are some commonly given cons for generative music. It's not widespread in the industry, and often the cons are given that these systems are technical and precise to use, that the quality is difficult the quality also in terms of the real-time synthesis is not as good as, say, a recording, and then also the musical quality is difficult to control, the compositional quality. And it's hard to get what you want out of these systems. It's often hard to control. And most academic approaches to using generative music in games mainly focus on trying to address these cons via the application of some new technology, some new algorithm that maybe is a little easier to use or that might have higher musical quality, under the assumption that if the technology is sufficiently advanced, we'll be able to sort of just plug these systems into a video game and it will work. With our work, we take a slightly different approach. Instead of focusing on trying to solve these problems with technology, we instead focus on looking at how we might use this technology to support a game, how we might actually apply generative music. So to give some examples of what I've been talking about, we'll listen to some academic approaches first to generative music in games. This is from Anthony Prechtel in 2016. This is Escape Point, and as we'll hear, we hear a single organ that plays chords that tries to match a tension value. Tension value is derived by how close the player is to these boxes that go through a maze. So we'll see. Okay, so that's Escape Point. We also have Metacompose. I don't have a video of this one. This was implemented into checkers, where the way that this Metacompose attempts to adapt the music based on valence and arousal, where those values are derived from a competitive AI that tries to see how good the checkers board position is for the player. And it produces music for a solo MIDI piano that sounds like this. This is a neutral piece. And then we have a higher valence piece. It's definitely higher valence. Now to compare this, let's look at something from the industry. This is taken from No Man's Sky, and we'll see a couple of musical transitions here. And it goes on like that. So as I mentioned, we did our survey of uses of generative music in both academia and the industry, and we found some trends in their approaches. On paper, the academic systems are great. They have generic emotion models that allow them, in theory, to be placed in a lot of different game environments. Their granularity is very high. They're able to adapt to what's happening in the music very fast. When we compare something like No Man's Sky, and we're just, it fades out and fades in over the course of seconds. And then academic approaches tend to use these really cool, advanced machine learning-based, often, algorithms that can generate really interesting music, whereas the industry tends to just combine written clips in new ways. However, I will note that the industry, in terms of the production and the performance value, tends to be a lot higher. If you had to ask me which one of those scores I would like to listen to, for a 20 or 40-hour game, I would pick No Man's Sky. In fact, it's not just me that thinks this. So Duncan Williams and others did a study in 2017, where they compared a linear score from World of Warcraft, the one used in the game, which is a recording of an orchestra that has a relatively flat and even emotional expression, to a generative system where the generative music had a valence and arousal value based off of, whether the player is in combat or whether they're completing a quest or whether they're just wandering. And participants found, they only had 11 people take part in the study, but generally what they found was that the emotional congruency ratings of generative music were higher, slightly higher than the emotional congruency ratings of the original flat orchestral score. However, in ratings of immersion, the generative score was rated significantly and quite a bit lower than the linear score in World of Warcraft. So people were finding that, yes, the generative music is matching the emotion of the game, but again, to put it informally, they wouldn't want to be playing World of Warcraft with the entire generative score or entirely with just the generative score. So what our goal with this research is to try to build a bridge between these two approaches and to try to use all of the advantages of academic approaches to generative music and all of the technological advancements that have been made. And we're trying to apply them in a way that actually fits into something that resembles an industry use of generative music, or really any industry uses of game music. So in order to do this, we had three main requirements. The first one is we needed a game. And because we wanted to do research on this, we wanted a game that was pretty easy to learn so that we could have participants come in, learn it, do something with it, and then leave. We also wanted to have a lot of control over what happens in the game. We couldn't deal with too big of a possibility space. And then we wanted to have all of the information coming from the game. We really wanted to be able to get into what was happening in the data of the game. And the reason we needed that was for a second requirement, which is that we wanted some way of translating what's happening in the game to a model of emotion. And then we take that model of emotion and we want some way of translating that into music. In theory, when we have all of these, what we get is people playing a game where music would feel like it is watching the game and matching the emotion, the perceived emotion. So our game is Galactic Defense. Again, we created this game. It takes about 5 to 10 minutes to play through once. It's a very stripped down sort of action RPG that's based a lot in counterplay and reacting to what's happening so that we are actually watching what's happening most of the time. That's very event-based. Now, as we mentioned, we need some way to translate the game into our model of emotion. Often in generative approaches, we use emotion models for experience-driven procedural content generation, where a piece of game content is being generated to create a particular experience in the player. Because we're trying to model the emotion of an audience member rather than the player, we're actually not concerned with the player loop. And so we create Preglam, which tries to do this much more direct line where it watches the gameplay. Instead of watching the visuals, it's watching the game data. It appraises the input. Again, instead of doing this in its brain, it does this using a computational model, and then it outputs an emotional perception. In this case, it outputs a modeled emotional perception. Preglam has two layers. Preglam is a layered model. So the first layer we should talk about is the mood layer. The mood layer is not quite strictly speaking the psychological version of mood. We can't tell if the player has been having a bad day before playing the game, but we kind of use the metaphor of mood to describe the more environmental aspects of the perceived affect. So our examples here we have from Bloodborne and from Elden Ring. The images are very similar, but you can see that the mood is different. One of them is a little more dark and foreboding, whereas one of them might be brighter and more hopeful. Preglam will always constantly trend towards the mood values. And in fact, if no gameplay is happening, Preglam's output will just be the mood value. This allows designers to sort of say, this is the emotion of this part of the game or this particular fight. To describe what's happening in the game, we use what we call emotionally evocative game events, or EJAs. Now, EJAs, I'll start backwards here and start with the time ramp value. This one's pretty straightforward. When Frida et al. Were studying most people's perceptions of emotions through time and asked them to chart how their emotions evolve through time, most people say, it kind of comes on and then peaks and then goes away linearly. Generally, the fade is a little longer than the oncoming part. So we just model this directly by having the emotional responses to any events kind of raise up linearly and then fade linearly. To describe the actual event itself, we use these two variables. One of them is the base emotion value. This describes what the event is. So if the player is getting hit with an attack, we assign this a negative valence. We do not want the player to get hit because they're trying to win the game. The context variable describes what this actually means to the gameplay. So getting hit, we might say, is a negative valence, but getting hit for 10 hit points at 100 health versus getting hit for 10 damage at 11 health or at 9 health have very different emotional intensities in terms of what we perceive. And so the context variable helps us describe that. In this case, if the opponent is attacking the player and their shield is full, that's a negative valence. But if the player's shield is almost empty or it is empty and they're about to start taking health damage, which is much more serious in our game, then the negative valence is twice as strong. It's amplified by the context variable. So preglam is a predictive model as well, and this is mainly to model tension. We're based off of the appraisal model of emotion presented by Ortoni, Clore, and Collins, where they describe tension as arising from perspective actions, from actions we expect to happen. Preglam predicts actions in two ways. One is it has access to privileged information. So the opponent AI is actually making decisions often earlier than it will tell the player. If it's about to use a heavy attack, for instance, it will tell the player, it will do a little red beam, and it will show the player that it's going to attack about 2.5 seconds before the attack. It will have actually made that decision 10 seconds before the attack, and that's when preglam learns about it. This allows preglam to be matching the emotion value or ramping towards the emotion value of that event by the time the player is aware of it and expecting the emotional change. Preglam also models based off of expected behavior. So this is for the player. This is because we can't predict exactly what they're going to do. This is based often on basically what we would expect the player to do well if they were playing the game correctly. So if the enemy is open for exploitation and the player would need to use their heavy attack to do that, preglam will create a prospective event and hope that the player is going to use their heavy attack. If the player doesn't, then this is simply a disconfirmed hope, and that also fits within the OCC model of emotion. For its output, preglam produces an unbounded continuous floating point value per emotion with a 250 millisecond time step. This is mainly to match our evaluation software, but also it also matches the Pagan database, which we took a lot of inspiration from in terms of our design. And so that we'll talk about how we evaluate that in a little bit. The next thing we're going to talk about is how we turn emotion into music. So we have, as we mentioned, 3 scores, and these are all produced. They all have the same instrumentation. They all have the same production quality. The only difference is the source of the music and the adaptivity of the music. So we have a linear score, an adaptive score, and a generative score. Now, our generative score uses the multi-track music machine, which was created by Jeff Enns here at the Meta Creation Lab. And as we can see, the way that it works is that you can upload a MIDI file to it, and you can select parts of music or select particular instruments and generate new music. It will replace the music that you've selected, and it will be conditioned on, it will be based on the surrounding musical context. So what this means for us is that when we're trying to control the output of MMM, we don't do it just by fiddling with parameters or setting some definition of theory, but by giving it music that expresses a particular emotion strongly enough that we believe that MMM will give it back to us. So in order to create this, we needed a way to compose music that would express a particular emotion. And we wanted to base this, obviously, as much as we could in the literature on music and emotion research. Now, a problem with music emotion research, similar to games music in general, is that there's a lot of terminology. And so most of what the ISOVAT guide does is it takes all of these spread studies and knowledge from music emotion research and tries to bring them into this single scale where we can look at a set of musical features, and then we can look at an ordinal relationship that changing those musical features has on the change of emotional perception. So for instance, if we are decreasing harmonic consonants, we will see an increase in tension because it is negatively correlated and strongly. So we use the ISOVAT score to create our adaptive 3-dimensional score. Our 3-dimensional score is set up in a 3x3x3 cube in valence, arousal, and tension space. So we have 27 clips. It is split into two musical sections. So there's the rhythm section and the melody section. This actually is for two reasons. One is to create the generative score, which we'll explain when I talk about the generative score. And the other is that this allows us to do some extra musical adaptivity to make transitions a little smoother, at least hopefully. So the melody section actually adapts at lower threshold values than the rhythm section. So we can have from a medium valence to a high valence. In the middle, we will have the melody playing the high valence and the rhythm playing the medium valence. So we'll call this a medium high. And then we can also go the other way. So this ends up taking us from a 3x3x3 grid into 7 unique arrangements for each level of each emotion. So one thing that we did with the adaptive score is we took all of the clips of the adaptive score and we wanted to create a linear score that again matched the adaptive score in terms of production quality. So the linear score is pretty much composed of the adaptive clips from the adaptive score laid out into a line. I did do some composition for the transitions and I did specifically lay them out so that it was an arrangement, but I tried to not touch the musical content at all. And we'll hear some examples of it right now, actually. So that's a low level of valence, arousal, and tension. Here we have a little bit higher valence and a little bit higher tension. It's a little more ambiguous. It's not quite so minor. Here we have one of my favorite transitions, which is the transition into, at about 60 seconds, we'll see the transition into higher arousal. Okay, and then finally we have the transition at about 90 seconds where we'll hear the valence and the tension really swap. We'll go from a really high tension to a really low tension and a really low valence to a really high valence. Okay, so that's our linear score. And then finally, as I mentioned, we have our generative score, the subject of this thesis. So in order to create this, as I mentioned, we took our adaptive score as a base and we used MMM. So what we did is we conditioned all of the new melody tracks on the existing rhythm tracks, and we conditioned the new rhythm tracks on the existing melody tracks. This meant that within any arrangement, we could substitute any of the melody tracks with any of the rhythm tracks, and then we can also mix them all together because MMM is always dealing in that musical space. And this works with our extra adaptivity of half levels. So what this ends up doing is creating about 14 trillion unique arrangements of music. So we're not quite getting real-time performance, but for the player, they're unlikely to hear the same piece of music twice, certainly. And just to have an example, we have a short video playing. I want to point out 3 main sort of moments that you might notice the generative adaptation. One is that the player is going to miss firing a heavy laser, then the music can get a little confused. When the player wins a battle, we'll hear the music get a little higher valence and do sort of a victory theme, and then it'll come back into the battle theme as the player gets back into the next battle. So let's listen and watch. Okay, so that's our generative score, and that's basically everything that we built and everything that we did. So the only thing that I have left to talk about is our evaluation. We did do an empirical evaluation of preglam and our generative score. For our empirical evaluation of preglam, we took inspiration from the work by David Melhart, Anthony Liepis, and Georgios Ioannakakis with Pagan, where we have players first become familiar with Galactic Defense. They play the game for about 20 minutes, and then they watch videos of gameplay. This is not videos of their own gameplay, but it's videos we took of gameplay. and they annotate using their arrow keys a real-time perception of an assigned emotional dimension. So in this GIF, we have valence. So what this does, this has a 250 millisecond time step similar to preglam's output, and the values are unbounded floating points. So what this gets us, at least in theory, is the ground truth version of what preglam is attempting to model. This gets us the ground truth annotations of perceived affect from gameplay. To analyze preglam's output, we had these big, giant, long time series. And so we used dynamic time warping, which gives us the closeness of the contours between two time series. We also used root mean squared error, which gives us sort of a more absolute distance between the two time series, but the findings were essentially the same. So I'll mostly talk about DTW here. Preglam, the dynamic time warping gives us a distance value that doesn't really have any absolute meaning in our unbounded floating point values of preglam. So to add an absolute benchmark measure, we included a random walk. What these charts give us then is the distance between preglam's annotations and a ground truth annotation in green, and then the red is the averages of the distances between the random walk and the ground truth annotations. And so preglam does significantly outperform a random walk. It does model the user perceptions or the player perceptions or the audience perceptions of gameplay. It does model it beating random walk. So it does work. This is not affected by different music, although the distance actually increases as music is added to the game. Our explanation for this is basically just that the music is also expressing some affect, and it might not be adapting as fast as if you're just watching what's happening in the gameplay. And so the user annotations might be a little bit confounded by having two different sources of emotional perception, even if they're relatively close. I'll also mention that preglam does not significantly outperform random, although it does outperform the random walk in terms of the dimension of valence. Valence is a very difficult emotional dimension to model, and this is consistent with other research in the area. In addition to doing the real-time evaluation, we also had a post hoc questionnaire that is modeled after the previous questionnaire from Duncan Williams, although we changed some of the things about the questions. And we found that our generative score was pretty similar, actually. It was rated slightly lower than for all categories, but in a close second, except for matching gameplay to our linear score. Now, at first glance, this is pretty discouraging compared to some of the other results that we've seen, but I'll reiterate here that when we're looking at emotional congruency, we're looking at emotional congruency between the generative score and a linear score that similarly goes through, using similar musical changes in musical features, similarly goes through various affective expressions in a way that the Williams study did not look at. For the World of Warcraft score, it's relatively flat. And I'll also note that while our immersion rating is still lower for our generative score than our linear score, it is much closer than the previous attempt. So this does seem to indicate, to me, what this indicates is that we were relatively successful in implementing generative music into the game. It is still not quite up to the quality of linear music, but we certainly made a good attempt. And we did basically what we set out to do, which was keep the emotional congruency and keep all of the advantages that academic approaches to using generative music had from previous studies, but make the music resemble something a little bit more like what game music might look like, so that we can look at it in more of a real world setting or something that mimics a real world setting. And with that, that is my thesis on the application and evaluation of generative music in video games. Thanks, everyone. Bye.